Hi, everyone. We'll get started. I'm Dave Judy, your host today. Welcome to the PNNL Grid Resilience webinar series. In this series, we're excited to share with you some of our current research efforts here at PNNL that are addressing grid resilience that considers both climate change and clean energy transitions. If we go to the next screen, Jeff. So this screen is illustrative of a roadmap to capture grid resilience to climate extremes. Over the next several weeks through this webinar series, we're going to hear about research efforts that focus on characterizing future weather events relative to grid resilience, things like wildfire, hurricanes, and wind. We'll also discuss some exciting new research around tool development used to represent technological change in our energy system portfolio and what that means for grid resilience. Today, we're excited to kick this off by first hearing from some of our grid infrastructure experts who lead research in the development of our grid reliability and resilience tools. And it's my pleasure to introduce Jason Fuller and Jeff Daigle to you. Jason joined the staff at PNNL as a research engineer in 2009 and currently serves as the group leader for the electricity security group. Mr. Fuller's area of interest include power system modeling, co-simulation of multi-domain problems, distribution automation and analysis, and integration of advanced distribution level technologies. He's led the development of a number of unique power system tools such as GridLab-D, Helix, and NARM. Jeff Daigle has worked here at PNNL since 1989. During that time, he's led numerous projects in the areas of transmission reliability and security. His recent project highlights include leading the development of the North American Synchrophaser Initiative and serving on the leadership team of the DOE Grid Modernization Laboratory Consortium, leading the multi-laboratory system operations and control technical area. He's a senior member of the IEEE and a member of the National Society for Professional Engineers. He received numerous awards for his work in the grid space, and Jeff holds several patents. So we're excited to have both Jeff and Jason here to present to us. With that, I'll turn it over to them.
Thanks, Dave. Appreciate it very much. And it's our honor to be presenting to you today on grid resilience. And to start with, I'll have a quick introduction of, if you're not familiar with the Pacific Northwest National Laboratory, of where we are and where we come from. So PNNL is one of 17 national laboratories across the country that support the DOE in various missions and critical to the future of the power of the nation. And specifically, PNNL was started in 1965. Currently has about $1.2 billion of research projects with 5,300 staff that are working in a variety of areas. And in the energy space, we support an energy environment mission. And that includes Jason and I working in the grid infrastructure area, but we also do a lot of work in energy security, emergency response, energy efficiency, supporting renewable energy, nuclear power regulatory support, carbon management and fossil energy support, as well as environmental management. So there's a number of mission areas that PNNL that are going on all the time. And so what we wanted to do today is focus in on electric power resilience to support this inaugural session of the Grid Resilience webinar series. And so I'll start with a little bit of an overview of how the power grid works, just to orient everybody. We have a number of people with different levels of experience on the webinar. So I just wanted to give some background information to fill in the basics. And then we'll dig into what is resilience and how is it different than grid reliability. There are some specific nuances there that we'll get into. I always like to learn from prior events, and so I've chosen 3 events to talk about in the past. So in '96 and 2003 and last year. And I'll share with you a National Academy report on technologies to enhance system resilience, and then we'll get into some of our research activities, and Jason will wrap us up with a discussion of the North American Energy Resilience Model tool that we're developing for DOE. So I like to start with this slide. Back in the turn of the century, the National Academy of Engineers listed the top 20 innovations that were most impactful during the 20th century. And widespread electrification of society was listed as the #1 technology that benefited the most people. And if you look at some of the other things on the list, many of those also depend on the grid. So the grid truly is one of our most critical infrastructure that we have in the country. And when we talk about the grid, it's really multiple grids across the country. We're very interconnected with Canada. And so if you look at the gray areas where we are here in Washington State, there's multiple states in the US and 2 provinces of Canada. The yellow color is what we call the Eastern Interconnection. The little green area down in the bottom is the grid of Texas. It's within the state boundaries of Texas. And then Quebec is a separate grid as well. And so Quebec likes to be independent, just like Texas. So they have their own different grid. And the only way to move power between those grids is to convert the 60 hertz AC to DC back to AC. But within each of those synchronous grids, the frequency is the same. So if I plugged in a meter here in Washington State and I looked at the frequency here and compared it to the frequency in California, in steady state, it would be all the same frequency because it operates as one big machine. Everything in that grid is interconnected and operates synchronously together. And then the power system has multiple components. There's generation, where the electricity comes from, different sources of energy, either from coal plants, natural gas, nuclear, hydro, wind, solar. There's a variety of technologies that are used to generate the electricity. And until a few years ago, about half of our energy was coal, but that fraction is rapidly reducing. Right now, most of our energy in the country comes from natural gas, but that is regionally different. So here in the Northwest, vast majority of our energy here in the Northwest is from hydro. But across the country, it's closer to 10%. Transmission, that's the high voltage interconnected network that connects the power generation and the substations together into the interstate transmission network. And that generally is defined as above 100,000 volts of energy. And then distribution is from those substations to the customers. And then we have the end use loads. And roughly this fraction is held pretty constant for a long time. Roughly a third of the energy goes to residential customers, a third goes to commercial customers, and a third goes to industrial customers. So there's a lot of different people out there that rely on the electricity. And then across these interconnected systems, there's about 150 of these control centers that would be collectively operating the grid. And the job is managing in real time, balancing the supply with the demand. Anytime that those are out of balance, the system either speeds up or slows down. And so that 60 hertz frequency is the nominal frequency, but the real frequency can be slightly different than that. And the eagle-eyed observer might see in this picture here that the frequency when this picture is taken is 59.994 hertz. And that's common for it to be close to 60, but not exact. So that's a real-time balancing thing that happens all day, every day, and it's done automatically, but then the human operators are involved in monitoring these. But really where the human operators get more involved is during emergencies or recovering the system. So when we talk about some of these grid resilience things, keep in mind the critical nature of these control centers. And generally they correspond with large utilities, would have these control centers. And so if they're a transmission network to utility, they are definitely interconnected with their neighbors and collectively operate the grid together. So in the Western interconnection, we have about 30 of these what we call balancing areas that work together to run the grid. Another thing that is very important to understand about how the grid works is things happen very quickly. There's some things that happen at the speed of light, traveling waves propagating down a transmission line, for example. There are disturbances that would propagate through the grid. It's a little bit slower than the speed of light, but it's still pretty fast, about 1,000 miles per second. And that's far too quick for us to manage. Even with automated systems, you can't manage these disturbances after they occur. So all grid operators worldwide do what we call contingency analysis, where they look at credible contingencies. So contingencies are what if scenarios. If this generation fails, would the system result in an uncontrolled cascading failure and collapse the grid? If this transmission line fails, would that cause a problem? And so we look at these contingencies. The shorthand is n-1, removing one component out of the n components that we have in operation. That's kind of a shorthand. In reality, it's a little bit more complex than that. The standards have 7 layers of contingencies that utilities assess, and that's kind of a standard that they've agreed to, with different levels of severity, and that combines the likelihood and the consequence. So a more likely thing, you don't want to have any severe consequence. Things that might be more rare, like a combination of things that might happen, but you still want to consider it for risk management purposes, then you might allow some things like shedding load or something to protect the grid. The other, I don't want to get into too much detail here about some of the measures, but they're all very important in terms of spinning reserve. That's more generation online than you need at any given time. Having emergency controls. So anytime that the frequency is higher than the generation, that means we have too much frequency is high, that means we have more generation than load. If frequency is low, we have not enough generation. So if we need to trip generators to protect them from damage, that would be a bad thing if we've already got a low frequency condition. So utilities install things called under frequency load shedding to try to have an emergency control to bring that back up to stable operating. And all of these things are done with prioritization. Number one is safety. So these high voltage equipment can be very dangerous if they're not operated correctly. So protecting the workers, protecting the public, that's highly important. And so these overhead transmission lines, for example, when they get overloaded, the heat in the conductors will sag and create a hazard to the public. And so that's never allowed to happen on purpose. Protecting the equipment from damage is also very important. When we talk about resilience, the time to restore the system is very critical aspect of this. So if the equipment gets damaged in the process of trying to maintain reliability, that's not a good outcome. And so protective relays and protective equipment are designed to trip things offline to protect them from damage. So that's the main job of circuit breakers and protection to protect that damage. And then maintaining the reliability of the system, and then optimizing the system to extract as much economic value out of it by trading energy over wide areas and things like that. So safety and security, I really like this diagram. It came out of a National Academies report last year. But safety and security are never deliberately compromised. We have standards and requirements to meet. But the other three, where you're looking at affordability, how much you pay for the electricity, how reliable you make it in terms of how much redundant equipment you can afford and things like that. And then how to tap into things like clean energy and making it carbon free or renewable. These often are trade-offs. And so the system operator might have choices to make in terms of how much to invest in sustainability or resilience or reliability. And if you're investing more money in that makes the electricity more expensive. And so all of these trade-offs are in play all the time with decisions that system operators and planners need to make. So that's an important consideration. So, we can't always have all three of those aspects at the same time. So I'm going to dig into what is reliability and how and resilience and how are they different. So to start with, we need to understand that there's a lot of different types of threats that we want to protect against, whether it's weather or human induced. And there's a number of reports and past events to think about. That picture in the middle was an ice storm in Canada that took out high voltage transmission lines, and that is really difficult to recover from because that takes a long time to rebuild those. But storms and hurricanes and earthquakes, these are all things that happen all the time. This is a picture. I'm the one in the blue shirt there with my colleague from the Department of Energy. This is south of New Orleans in 2005 following Hurricane Katrina. And you can see the substation here is completely thrashed, and that is a result of storm surge. So where we're standing there was completely underwater during the storm, and very much devastated this entire area. And so where we were here, and this is many weeks after the storm, 6 weeks after the storm is when this picture was taken, there was no electricity service anywhere near us. This whole parish in Louisiana, they call them parish, it's like counties, was out of service at that time, 6 weeks after the storm. So just put that in perspective. When there's a lot of physical damage, it takes time to recover. Restoration, if there's no damage. So the first thing is to fix the damage if there's damage. The other thing to keep in mind is a lot of power plants require offsite power in order for them to function correctly. Nuclear plants are very, in particular, very important to have offsite power. And so when we saw the problems with Fukushima and the concerns lately here in Ukraine, when you lose offsite power, and then you rely on your backup diesel generators, and if they fail, then you have problems cooling the spent fuel, and you can have overheating and a problem with that. And so that's exactly what happened in Fukushima, because the tsunami took out the backup generators and the power feeding the plant. So offsite power is very important, but even non-nuclear plants, large plants, would require offsite power in order for them to operate. And so the black start restoration process, when you do have a complete grid failure, is you need to feed what you have to those power plants, get them going before you can start picking up your load. And then, of course, it's obvious that you would restore load with your critical loads first. And there's a lot of definitions of grid resilience out there. This is my favorite, but it's the ability to reduce the magnitude and duration of disruptive events. And these disruptive events are all hazards. So it's like I mentioned earlier, it could be weather, severe storms or things like that. It could be cyber attack, physical attack. It could even be weird off the wall things like geomagnetic disturbances from the sun that creates a problem on the grid. And Quebec in Canada had their grid collapse in 1989 as a result of a solar storm. So all of these types of things are important to keep in mind. And then there's a report in 2010 on establishing critical infrastructure resilience goals. And what's really great about this is that this diagram is it doesn't focus on just restoration. It doesn't focus on just hardening before the event, but it's a holistic way of looking at this resilience cycle where we manage the event, but we've got good preparedness, we've got good recovery, but then this adaptability and lessons learned feedback loop is also important. So when we do have events, we learn from those to apply those lessons in the future. So in that vein, I'd like to talk about 3 examples. There's many examples to choose from, but these 3 are particularly interesting to me because they all kind of have different things that went wrong and things that we can learn from. So if we go back to August 10th, 1996, here's a diagram of the Western power grid. It was a hot day, especially in California. They were really eager to import power from the Northwest. That spring before, or that winter before, we had a lot of snow in the mountains. So we had a good snow pack and spring runoff of our hydro system. So we had a lot of power available to sell, and they wanted to buy it that day. And what's kind of shown in the diagram here between Seattle and Portland is that there are some assets out of service, electrical assets out of service for maintenance. And so through Eastern Washington here, the grid was under stress. We lost a couple of transmission lines about 5 minutes apart from each other. Losing one is fine for that credible contingency that I talked about earlier. But when you lose 2, and then there's a generator that tripped off, the McNary hydro plant, which is right on the border between Washington and Oregon, not far from where we are here in the Tri-Cities, that created this undamped growing oscillation. And that ripped the grid up. There was 4 electrical islands that were formed. So the Western interconnection broke apart into different islands. And depending on whether you're importing or exporting power before the event, that was whether or not you had a big blackout. So California and Arizona areas were importing a lot of power. So they took the brunt of the outage across the Western interconnection. It affected about 30 million people that day. The root cause of the transmission lines was the tree trimming near the transmission lines wasn't maintained well enough. So we had a ground fault with the lines getting into the trees and tripped off. But this is a big one. The red is the measured data. And so this is the same data I showed a little bit a couple slides ago. And then the blue chart here is what the computer models would simulate with that same sequence of events. And so all those contingencies that I was telling you about, those are based on computer models. And the computer models predicted that the grid should not have had a problem. And obviously the grid did have a problem. And so this led to a lot of work to improve the accuracy of those computer models based on taking better measurements of the power system. And the oscillation, the frequency of this oscillation here is about 0.3 hertz. So very low frequency, but it when it gets going, and it's undamped like that, that creates a lot of problems in the power system. So that was a big deal. This data right here showed that there was a need for model validation, and the U.S. Department of Energy, working with labs like Pacific Northwest National Lab, got involved working with the electric utility industry to not only get better measurements, but also use those measurements to improve the accuracy of the power grid models. So that was a very important blackout to learn from. The next one I'm going to feature is the largest blackout in the history of the North American grid. This affected about 50 million people back in 2003. It happened in the northeast area of the U.S., but also included Canada. So it really started in Ohio, but it affected places like Detroit, Toronto, New York City, and so it was a big deal. Created a lot of disruption. This is a diagram that shows the hours leading up to the blackout. The blackout occurred just shortly after 4 o'clock in the afternoon. But the real key event, even though there's a power line that tripped earlier in the day called the East Lake 5 unit, the real important thing that happened was right after 3 o'clock. That little line down there called Harding-Chamberlain, when that tripped at 3:05, that then created a condition that the system was no longer safe to additional outages that might occur. And additional outages did occur. But the problem is the system operators in that control room, so that picture of that control room I showed earlier, those system operators did not know that this was happening because they had some data problems. So there's a computer problem, there's a glitch with their computer. They weren't seeing the data that was happening. And so they were kind of flying blind as the system unraveled and fell apart. But it took about an hour. So that's kind of another key lesson of this. It took about an hour for the system to collapse between when they really had a significant problem to when it had the uncontrolled cascading failure and took out the rest of the system. So to me, that's remarkable that the system kind of would run for about an hour under that dangerous conditions. You always think of the grid as, you got to be right on top of things, and things happen really fast, but sometimes it takes a long time for these problems to spiral out of control. So this sort of shows the sequence in the chart I showed in the previous slide. This shows it kind of on the map. So these lines that were shown in that chart are kind of right in here in the middle of Ohio. And that little red dotted line that goes up Ohio and up the middle of Michigan, that was the separation of additional lines that tripped with the cascading failure. And it created a power flow reversal going around Lake Erie through Pennsylvania, New York, and took out more transmission lines. We ended up with multiple islands that were formed. Upstate New York kind of held in and did not go out. Up in New England, they separated from the grid and didn't go out. So the blackout area was pretty well contained to northern Ohio, Detroit in the eastern part of Michigan, a lot of Ontario, so Toronto and areas of Ontario, but then not upstate New York, but the New York that included New York City. And so that was kind of the footprint of the blackout. This is a really cool plot. This shows frequency, so that 60 hertz frequency, and showing you kind of how it can vary during a large disturbance. This is data from different areas around New York, and you can kind of see that the area of upstate New York here survived and stabilized, and areas of New York that included New York City did not. So all the underfrequency load shedding was exhausted by this point here, about halfway into the plot, and the system, that part of the system collapsed. This part of the system survived, and this diagram here shows a really great illustration of how it broke up into multiple islands during that process. Many generators were tripped during that day. The good news is that all of these generators did not sustain any damage. So as soon as you got the grid back on, then you can bring these generators back online and start serving load again. But this shows the first stage of generator tripping, and then the second stage, more generators around the Lake Erie and kind of the Detroit area. And then by the time the dust settled, there's over 500 generator plants that tripped offline. So that shows the area there. The Blackout investigation team worked for many months on developing the root causes. So root cause number one was the system operator didn't really have a good plan for what should have happened. And so lack of rigor in terms of the engineering preparedness for this. Root cause number two was the lack of situational awareness by the first energy operators. And so that was another root cause associated with that. And then root cause number three was, and that was the data problem I was telling you about. Root cause number three was inadequate vegetation management. So these are the transmission lines getting into the trees again. So that's pretty similar to the 1996 one. We did, on the Blackout investigation team, we did have a question about whether or not the wind speed might have had an issue because it was not windy at all that day. Akron Airport, near the epicenter of all this, reported 0 knots wind speed at the airport at 3 o'clock in the afternoon and at 4 o'clock in the afternoon. And the industry standard for rating overhead transmission lines is you assume a little gentle breeze to help cool the conductors. And so that was a concern. Did we make a mistake in terms of rating those conductors by not assuming the possibility of 0 wind? And the conclusion came out that no, it truly was that the trees were allowed to grow too close to those overhead transmission lines. And then root cause number 4 was there's a layer of organization above the utilities called reliability coordinators, and their job is to prevent things like that from happening. And they had a failure on that day as well. So the third case study I'd like to talk about is what happened in Texas last year. So Texas experienced a very significant power system event where they lost about half of their generators in the state. And their grid is a little bit smaller than the east or the west grids. It's about an 80,000 megawatt system, and they lost about half. And the grid operators, in order to save the rest of the grid, they implemented what's called load shedding to maintain that balance. And so again, this is that same frequency I was telling you about. That's a very important parameter. But this shows frequency is maintained at about 60 hertz, and these are in 10-minute sort of intervals here along the bottom. So very quickly, just over the span of a few minutes, the frequency is dropping because in the green dots here, we have generation outages, and the red dots are load shed. And so the system operator shed enough load to bring the system back to stable operation. So that saved the grid, but unfortunately, in order to do that, you had to turn off about half the customers because you lost about half the generators. And so that wasn't a good event. And they couldn't bring them back until things thawed out a little bit. A lot of the problems were in the natural gas infrastructure, but there was coal units that tripped because they had some things freeze up. They even had a nuclear plant that tripped because of some water supply instrumentation lines on the feed water supply froze up. So there was a lot of problems that occurred. They had solar that was covered with snow. They had wind that was out because the turbines were iced up. Just about every generation technology imaginable had problems that week. And then you can't, the problem is you can't bring the customers back on until the system is restored. And so this shows the outages by fuel type. And so natural gas is this green one here. So 25,000 megawatts of generation not available because of problems in the natural gas supply. So that's a big problem. A lot of people were wondering, well, how can this be? Because Texas had a cold event. Their last really big one was in 2011. And so this chart compares the 2011 on the left with 2021 on the right. And it's amazing when you see how much colder it got last year than the one from 10 years ago. So if you look at this chart, Dallas Fort Worth is this one in the blue. They got down to 13 degrees in 2011. They got to -2 degrees. These are Fahrenheit, -2 Fahrenheit in 2021. So trying to winterize a power plant to 13 degrees or -2 degrees, it's extremely more difficult when it's that much colder. So it's just so much colder than they experienced before. set new records by 10 degrees, in terms of the coldest weather that they've had before. So that was really kind of what caused it. They thought they were prepared. They thought they had the mechanisms in place to have those plants winterized, but it was just so much colder that they just couldn't keep up with the demands. And so that created a lot of problems on the generators. So I want to shift gear next. We are running really short on time, so I unfortunately tried to pack too much good stuff into a short presentation here. So that's not going to have time to really go through this in detail. But if you're interested in what we're talking about, there's a really great report from the National Academies, came out in 2017 on enhancing resilience of the power grid. And so a lot of almost everything I'm talking about, you can, obviously not the 2021 event because that happened afterwards, but a lot of things that I'm talking about are embodied in that report. But from that report, here's specific technology opportunities to enhance resilience. So hardening components, physical security, distribution automation, better computers and controls to redispatch the system. These distributed energy resources, that's often code for rooftop solar. Those can really help, but only if they're designed to operate in islanded mode. A lot of times these rooftop solar or other forms of distributed energy resource systems rely on the connection with the grid in order for them to operate. So if the grid goes down, they go down, and it just doesn't really help very much. But if the distributed energy resources is designed properly, it costs a little bit more, but it has some resilience enhancing potential if they've got the right kind of controls on there. Better modeling simulation, the one I showed earlier with the data that doesn't match reality, that's important. Data, through wide area monitoring, using that data for control. The load shedding and adaptive islanding is a technology that has a lot of promise. Architectural considerations to reduce criticality of individual components. So I have a colleague in the industry who's got a great saying. He says that the easiest way to protect your most critical substations is to not have any critical substations. And so the way you design the system to have the right kind of redundancy in place, there's a lot of benefit that you can get from that. And then what I like about that approach is it doesn't matter what the nature of the attack is, or the problem, or the hazard that you're trying to defend against. You're reducing your dependency on critical components, and so that really helps. Also reducing your dependency on supporting infrastructure. We saw that in Texas last year. Natural gas is becoming much more important to the generation of power. And we've evolved where we don't use as much coal, we use a lot more natural gas. Coal had a lot of on-site storage, natural gas does not. And so that creates a lot of new issues that we didn't have in the past. And then finally, cyber resilience. That's deeper concept than cybersecurity. Cybersecurity is keeping a problem from occurring. Cyber resilience is that plus, if you do have a problem, can you get your systems back online quickly? And so practicing that, having drills, having recovery plans and that sort of thing, it's an important part of cyber resilience. So next up, I'd just like to touch on this Grid Modernization Lab Consortium. Dave kind of hit on that in my intro. But what's really important is it not only brings together multiple national labs, but it also brings together multiple offices within the Department of Energy. So EERE, OE, FE, NE, and CSER are different offices in DOE that do different aspects of things that are related to the power system. But this initiative kind of brings this grid modernization initiative brings together a lot of those different people in those different offices to work on these common problems. So it's really great to have been part of this over the past several years. This was really started in 2016. And so it's something that getting together all these labs and all these DOE offices to work together has really been transformative. So next up, I'd like to turn it over to my colleague, Jason, to talk about some of the research that came out of that Grid Modernization Lab Consortium.
Thanks, Jeff. And we got about 10 more minutes of material here, and then we'll turn it over for questions. So we'll definitely have a chance to chat with Jeff here in a few more minutes. But I want to give you some kind of background here. One of the projects that came out of the Grid Modernization Lab Consortium was a project called Helix, which is a tool that was designed to start to evaluate the fact that our energy system is not just electricity anymore, but it's actually entwined with a lot of our other infrastructures. So if you think about natural gas and grid or telecommunications and the impact on the power systems, how do distribution and transmission work together, even starting to integrating buildings and DERs and transportation. All these things are all dependent on each other at this point, and we want to have a way to be able to evaluate and understand those relationships and dependencies as we kind of do a joint evolution of these different interconnected energy systems. And so this tool, Helix, was created with a number of national labs listed there on the right, but really trying to look at ways to support the best-in-class tools and models and data that we already have, and combine those in a way that allow us to do more than what we could singularly. So if you look at the kind of bottom right image there, talk about some of the things we've been working on. These are not creating new modeling environments per se, but looking at what we have in terms of best in class and then being able to put them together. So let me give you an example of one of those type of things and how we use it. Next slide, Jeff. Is some work that was done by some of my colleagues here. Wei Du is the lead of this, but really looking at how grid forming energy storage systems can improve the stability of the low inertia bulk system. And so really there you're talking about being able to connect to transmission and distribution models. So you see in the bottom left here, what we're looking is connecting a PSSE and then connect that to GridLab-D. So that's a commercial tool plus an open source tool. And then build new grid forming inverter models, and then use all of those to evaluate the dynamic stability of the system when you have high penetrations of inverter-based technologies. Go ahead, next slide, Jeff. And so when you put all these pieces together, you're able to understand then, well, what happens when you start to model these things and look at the improvement or not in terms of the stability of the system. In this case, you can see some very significant improvement around the grid frequency response when you actually have, in this case, 45% of the circuits have grid forming inverters. But part of the work that goes on, and there's a really great paper on this, is also to look at how much do you actually need? How many of the inverters actually need to be a resource and a distributed resource in the system to actually provide stability overall? And so this is really taking a whole bunch of different tools, combining them together without having to recreate the wheel. And so we feel that these co-simulation environments have a lot of value that allow us to stitch together different things and look at them in new ways. Next slide, Jeff. And so then the next example that we have of that is really kind of around DOE's North American Energy System Resilience Model. And so NARM is kind of what we call it here, but this is really looking at the fact that when we talk about our electrical system, it is so dependent on right now natural gas and communications as we modernize it that we just can't look at it in isolation when we're thinking about resilience. So DOE launched this, Office of Electricity launched this effort in 2018. So we've been working on it for about 4 years now. But the goal is really to try to predict energy system independency's consequences at an extreme scale. So we're talking about extreme events at a national scale. So this is going beyond, what a typical utility would look at from a reliability point of view, but look at big threats to our energy system to understand how the system will behave during those. And then more importantly, how can we mitigate them and understand that what improvements can we make to help reduce that impact. And so, one of the key objectives there is not only to look at these individually, but also then to catalyze different partnerships across the industry in ways that we can better coordinate and enhance our resilience over time. So to give you an example, we've created this kind of workflow that around NARM that has a lot of capabilities. So we're looking at a lot of different threats and hazard models. So anything from hurricanes to ice storms to man-made to wildfires. And we represent those as models into the system that then couple together these bulk electricity system models, natural gas communication models, with the idea that you're trying to then understand what are the outages that might be, what are kind of some of the post-event analyses that you might want to do, what are some of the operational planning options or other enhancements that we might want to provide. And part of what we've been doing over the last couple of years is starting to think about, well, what does the new system look like? So not only do we understand what resilience looks like today, but can we actually look at it from the perspective of tomorrow and understand what will large penetrations of solar, wind, batteries, or other elements, how will that change the behavior of the system? And I emphasize on this that these are really, these are domain models, but they're really detailed engineering models. So we're using tools like PowerWorld and PSLF to do both steady state and dynamic modeling, and equivalent models in the natural gas system and communication system that allow us to look at the evolution of some of these. So the next slide will just give you an example of how we used this last year in some of the some wildfire impact studies that we were doing for DOE. This was in semi-real time. I call it real time, but it was probably delayed by about 24 hours. You can see this was during some of the major wildfires across the West last year in mid-July. And what we're able to give an example here is the Dixie Fry case on the bottom right. Look at what was the perimeter of the fire system, where was the intensity of the fire, which power lines and or natural gas pipelines might be potentially threatened by those perimeter lines, and then try to understand if we had a failure in those zones, what would be the overall system-wide impact. And I always emphasize the fact that when we're talking really focus on system-wide impacts, because utilities are doing this in real time and trying to understand how to reroute power so they can maintain their stability and their requirements for reliability. This is trying to understand what is the overall impact to the wider system, and are there things that DOE should be aware of to make sure that things are moving forward. So this is really an integrated natural gas grid model. Second kind of case on this is really looking at some of the cold wave events. So this is a report we were producing about every other week, just depending on kind of what the weather was looking at across the United States, but really trying to understand what was the risk of load not served during weather events. So we're looking at some of the cold waves sweeping across the country. You can see here, this is an example from early February of 2022, where you can see a big cold wave is kind of moving across the Midwest to Northeast. And then identifying on the left what is the risk of different loads not being served due to a wide variety of different failures within the system, and trying to analyze what those pieces might be. You can see this. So from there, when we start to think about not only about the resilience of today's system, but then start thinking about what's the resilience of the tomorrow system. And you're going to see more of this as we move into some of the presentations over the next couple weeks, is really starting to think about the fact that we have a lot of really strong modeling in climate and earth systems, trying to understand how exascale Earth model, how it interacts with the water systems, how different decisions and policies make differences in how the Earth system behaves. And we also have a whole lot of work and a whole lot of good work that's been done in the grid modeling side of things, in terms of trying to understand expansion modeling, trying to understand like contingency analysis and dynamics and other elements. But what we don't have, go and click the next slide, Jeff, is something that actually combines the two together to start thinking about how do you really think about this Earth system and the overall climate, the overall water system, how humans interact with the Earth. How do you actually then tie that to the power system elements that we're and really kind of layer that into what I'll call a detailed engineering model to understand how it impacts planning and operations on the power system. So this is something that we're really focused on here at PNNL over the next couple of years, is trying to bring those best-in-class models together in a way that can provide elements of both in a way that are usable for our energy system. With that, I'll turn it back to Jeff to kind of wrap this up here and leave some time for questions.
Yeah, thanks, Jason. So, I think we've made the point here that the grid is a very complex system. But even though we've focused on times that it has failed in the past, I do want to remind everybody that the North American power grid is extraordinarily reliable. I mean, we get our grid, power works almost every day. And so given the complexity of it, that's a good testament to the men and women that really plan and operate that grid every day. But when we do have a failure, that's a really important opportunity for us to dig in and look at it very carefully. And I think that there's some other unintended consequences coming with more complexity and automation. So for example, cybersecurity is something that a lot of people are worried about. But when we look at resilience and we think about all the threats to the system and how we can design it to not only withstand those, but also bounce back from those, that's important. And I really think it's critical to have an all hazards approach to this. Don't just get fixated on, storm hardening, but, there's other things, storms and earthquakes and attack, those are all important. And finally, I hope that we've made it clear that there's a lot of R&D that is going on that is helping to move the ball forward on this. So that is our prepared remarks, and we're available now for a few minutes of Q&A.
Yeah, thank you, Jeff and Jason, for this excellent overview of the grid and some of the tools that are available. Feel free to continue to put questions into the chat. We've got one here to kick it off that I'll pass along. The question is, how do we overcome the trade-off between achieving resilience and added costs, specifically with relatively low frequency events and validating this cost for funding?
Yeah, no, it's a great question. And it's a very big challenge, right? Because when you're trying to protect something that has, large consequences, but maybe very rare, is it really a good investment versus something that maybe has, more often would occur, but maybe the consequences aren't as great. And especially when you're coming up with things that may not ever happen, right? In terms of this analysis, and is it wise to spend money on those types of things? And you won't really know until that event either does or doesn't happen. So one way to sort of answer that question without directly answering it is in that 2017 National Academies report on enhancing resilience, we point out that in the past, when you really invest in power system reliability, it's things that the utilities are doing to make those investments. That money is passed on to the ratepayers. But when you think about grid resilience, that has societal benefit because we want to have communities that are resilient and things like that. And so in the future, could there be more of a blending of ratepayer funded investment and taxpayer funded investment? And the precedence is there. So for example, following Superstorm Sandy, the state of New Jersey had grants for utilities and other critical infrastructure to move their infrastructure out of the floodplain. And so that was state funded grants, billions of dollars of grants to the critical infrastructure owners and operators to harden their infrastructure and move things out of the floodplain. So that's an example where there's taxpayer funded investment to improve the resilience of these systems. So I think in the future, when we really look at this trade-off, whether it's for the betterment of the customers, in terms of the residential, commercial, industrial customers directly, then it should be kind of ratepayer investment. But if it's for the betterment of society in general, and I think some of these protecting things from very large consequence events, but maybe very rare or unlikely events, so the low frequency, high impact kinds of things, that might make sense to be more taxpayer funded. So stay tuned for more on that as we evolve over the next several decades.
Thanks, Jeff. We kind of a follow-up question to that and digging in a little more on the trade-offs between achieving resilient decarbonization and equity in power energy systems. You had a slide on that. Question is, are these factors contradictory or complementary? How do you achieve all these factors considering all the market players that exist? You've got system operators, customers, service providers, and regulators.
Yeah, and absolutely correct and insightful question. And sometimes they aren't trade-offs. Sometimes it's a new technology that is available that then you can kind of achieve multiple objectives without necessarily having to trade off. So for example, if we have breakthroughs in terms of the cost of storage, storage is going to have a pretty big impact on enhancing reliability and resilience. And so if that gets more affordable, then that's a win-win. We've also seen that with the cost of some of these distributed generation technologies like solar panels, for example. Those are becoming the cheapest option in a lot of cases. And so, and you reduce your dependency on fuel, because it's there's no supply chain associated with those. So as long as you can accommodate the non-dispatchable nature of it, the fact that generation is only available when the sun is shining, and not available when the sun isn't shining, for example, that's still a significant drawback of that technology. Hence my comment about storage. But if the cost of that keeps going down like it is, that's a viable option that is really going to help out a lot and create a lot of benefit. Just it's very important to make sure that those resources are hardened. We had a lot of solar that was destroyed in Puerto Rico with Hurricane Maria, right? And so so hardening these so they can survive a hurricane and things like that, that's a critical part of the puzzle. But I think it's still an example where advanced technology is kind of helping move the ball forward without necessarily trading off between this or that. We can kind of do both. But coming back to the question, oftentimes there are trade-offs, and the balance then is a conversation between the stakeholders, especially utilities and regulators, right, and legislatures. If we bring in the state funding and you know, federal funding and things, there's a lot of stakeholders. It's very complicated.
I just want to mention, I agree with everything Jeff said, but just to add to that is I think that's one of the challenges going forward, is to try to make sure that we are able to address all these simultaneously. So right now it's often done by lessons learned, or by somebody going out and trying it and finding out that, oh, we had this unintended consequence. You know, the example that I always like to think about is, you know, where there was a lot of solar investment that then had to lead to you know, distribution circuits need to be upgraded to support more solar, but it was actually, you know, negatively impacting, or it was positively impacting high income earners who could afford the solar payouts and things like that. And so that's kind of the things that are right now are we're learning by lessons learned. We prefer if we can start to think about these as integrated modeling environments that allow us to address these ahead of time and start to think about what are all the consequences of all of our decisions, and be able to kind of unfold those and unpack those and understand, make sure that we're making the correct decisions going forward.
Speaking of modeling, Jason, I think a question that you might be well positioned to answer: how do you handle the level of complexity of each interconnected systems and assess the accurate interactions under extreme events?
Oh man, that's the tough question of the day right there. No, it's really hard. You know, you're talking about both the fact that these are extreme events, which means you don't have a lot of stuff to validate against, and then you're going to take two hard to validate models and combine them together. You know, I think at this stage, and we're still learning, we're still trying to do that. We're trying to use, you know, historical events to go back and try to replicate them as a way to then try to project into the forward. There's also a lot of kind of work that's being done right now in uncertainty quantification. So trying to say that we don't know how well these tools are, but can we understand how uncertain they are, at least, to give us some bounds on some of those questions. And so I think that's going to be kind of the question of the day going forward for a good decade or so, trying to understand how these big complex models work together. You know, we can take lessons from a lot of other industries and what they've done to do that, but at some point we just have to kind of give it a try and then check our answers as we're going in some ways.
In the case studies, presume the ones you talked about, Jeff, and other situations around extreme events, do operators in the US proactively shut down generating plants, or do the generators shut down automatically if their transmission lines fail? Chicken or the egg?
That's a great question. And it's a changing landscape. So and again, the real answer is it depends. So for example, one of the things that especially in California we've been seeing here lately is that sometimes high wind can lead to transmission system failure that can spark a wildfire. And so utilities, to manage their overall risk, will preemptively de-energize transmission lines to prevent that ignition source for a wildfire if the wind is, you know, above certain threshold. And so they kind of look at it pretty carefully in terms of that risk management process. I've seen some research, it's not adopted, but I've seen research where maybe if you had early warning of an earthquake, so sometimes you might, with new technologies, you might get, you know, 10, 20 seconds of advance notice of an earthquake. It might make sense to preemptively de-energize the network so that you have less damage due to electrical faults and things. So that's still research, but those kinds of things are in play. But for the most part, and with all of the examples that I gave in you know, I mean, the Texas event, the generation was tripping because of problems on the generation side, and the system operators then had to manually shed the load to kind of keep things in balance. But the other two case studies, all of the generation tripped it wasn't done preemptively. It was done with automatic controls designed to prevent the generation from getting damaged. And so that was the case where the generation just held on as long as it could, and it tripped off when it needed to prevent itself from damage with those automatic controls. So that's, for the most case, that's how it's set up and designed. You run the grid, you try to keep the grid going, you try to keep all the assets energized, and they only get turned off when they have to for protecting them from damage.
I'll throw in one last quick question, maybe a quick answer from Jeff or Jason. Is underground substation an alternative option to reduce chances of storm damage?
So undergrounding is indeed an option. It's done quite extensively. A lot of distribution is undergrounded today, and more is undergrounded. Transmission isn't undergrounded as much, but it is significantly more expensive to do underground versus overhead. So that's a very, very big trade-off. And so that comes into the affordability versus resilience. And then the other thing I'll point out about undergrounding is it helps a lot with things like wind, right? But in wildfire, those are great case studies where undergrounding helps a lot. Earthquake, not so much, right? And so the recovery time with repairing faulted underground is also longer. So the time to restore could be lengthened if it's underground versus overhead. So there's a lot of trade-offs, but the big one that people really have an issue with is the cost, right? It can be 5 to 10 times more expensive, especially when you get to the high voltage transmission. It's just not practical in a lot of cases to do it underground because it's so much more expensive. So those are very significant trade-offs that need to be factored in.
Thank you, Jeff and Jason. We're at the top of the hour here. Thanks everyone for attending, and thank you for your questions. I encourage you to attend the next seminar in our series of webinars here. We'll be talking about resilience to wildfires 2 weeks from today. And then in the future, other discussions around some of these extremes. So we look forward to having further discussions with you all. Thank you.